Sciences at Stanford University. In 2020, as you all know, Paul was named the recipient of the Nobel Memorial Prize in Economics and appointed as a distinguished fellow of the American Economic Association. His numerous other academic awards and honors appear on his website. Paul is also co-founder of Auctionomics, which designs and advises bidders in high-stakes auctions. Paul, first of all, a huge congratulations on your well-deserved Nobel Prize. We are excited to have you as our first speaker in the winter quarter. Before you start your talk, let me have a brief announcement or brief reminder for the audience. You feel free to submit your questions through the chat window during the talk, and we will relay them to Paul. If there are longer questions, longer discussion questions, you can also ask them at the end. Feel free to include them in the chat as well and mention that they are for the Q&A part. Paul, again, it's a pleasure to have you.
Okay, well, thank you. Let me share my screen here. So I'm going to talk to you today about a project that I'm doing with Mohammed Akbarpour, Scott Commoners, and Chenggu Li. It's called Investment Incentives in Near Optimal Mechanisms. Yeah, this version has the November 2020 date on it. It's actually the current version. I just didn't update the date. Okay, let's see. So we all know that if you come to the question of how you do efficient resource allocation with transfers, and you need to get information about values from the participants, if you ask the question who gets what and how much should they pay, the standard answer for many years has been Vickrey-Clark-Grove's mechanism. It's a mechanism where you ask people to report their value information and you compute an efficient allocation. And it's provably strategy proof, so it's in everyone's interest to report truthfully. And it also provides efficient investment incentives. If you think about an individual who's going to participate in this mechanism, if you change one bidder's value, then under the Vickrey-Clark-Grove mechanism, the change in that bidder's payoff is equal to the change in the bidder's welfare, is equal to the change in social welfare. So the bidder gains by investing, that is paying a cost that changes value, if and only if the social welfare also increases. We have efficient investment incentives in the Vickrey mechanism. Now, there are caveats to that conclusion. 3 caveats I want to mention. First of all, to make this choice to invest efficiently, the bidder must know or have good information about the prices that will be paid. You don't want to pay to do something that's unprofitable. When there's multiple investors, this conclusion isn't quite true. There are coordination issues that arise. If Martin and I are both have opportunities to invest, our investments might be profitable if we both invest, but not if just one of us invests, and there can be multiple equilibrium of an investment gain. And third, VCG mechanisms rely on exact optimization, and that's going to be the subject of today's paper. We're interested in hard resource allocation problems. In a VCG mechanism, the way you compute somebody's price is you compute the value of the resource allocation, including that individual, the optimal value, and then you compute the optimal value without that individual. And the difference is what is paid to the individual, is the profit that the individual gets in the mechanism. So it's the difference between 2 optimizations. And in the problem where I first became aware of this, in the FCC spectrum auction problem, the value of an individual station was about 1/2000th on average of the value of all the broadcasters. So if you were to make even a 1% error, an additional 1% error in one of the optimizations, you would misestimate the price by a factor of 20. 20, that is 20 times as high a price. I mean, the prices that you get that you compute in the VCG mechanism require really very nearly exact optimization. And many real-world allocation problems are NP hard. The spectrum problem I was describing to you, which is hinted at on the right here, with local interference constraints, was an NP hard problem, which was very difficult to solve. Combinatorial auctions, certain electricity auctions. And in practice, we often use approximate allocation rules. And so the research question that we want to pose today, if we do use an approximate allocation rule and a strategy proof mechanism, what happens to the incentives to invest efficiently in the various constraining resources? So that's the question we're posing. Now, an overview informally of our results is, well, first of all, is it necessarily true that if you have inefficient allocations and a strategy proof mechanism, will you necessarily have inefficient investments? That is, will people's investment incentives differ from those of the social planner? The answer to that question is yes, not too surprising. If you have a non-optimizing allocation rule, it has what we're going to call algorithmic externalities. Externalities is an economic term. It means that the change in your payment for a resource, or for using a resource, is not equal to the social cost. And if you have a non-optimizing rule, there will always be algorithmic externalities, and so there will always be the possibility of inefficient investments. A second question, and this is really the more interesting one, is what about if you have a pretty good allocation rule, it's nearly efficient, and you implement it in a strategy-proof mechanism? Will you have near efficient incentives? And here's the surprise, I guess, if there is a surprise in this paper. The answer to that is no. You can have an arbitrarily good approximate allocation rule, and it can have arbitrarily bad investment incentives. But if the allocation rule has a new property that's called excluding Bossy negative externalities, which I'll define later, X-bone, X for exclude, BO for Bossy, NE for negative externalities, then the investment incentives are okay. It means that you don't suffer any deterioration in worst case performance if the algorithm has this property. And the third result is a characterization result. Weak X-bone, which is a more complicated condition, is necessary and sufficient for the conclusion that you don't deteriorate, you don't make performance worse by including, in the worst case, by including an investment stage. Okay, so to illustrate ideas, we're going to have a running example, which is just a knapsack problem, standard easy problem. An instance of the knapsack problem specifies a set of participants or bidders. Each bidder has a value for being packed into the knapsack, and each bidder has a size, and the knapsack has a capacity. So in this example, there are 4 guys who have items they want to put in the knapsack. Guy 1 has a value V1, and the size of his item is S1, and similarly for individuals 2, 3, and 4. And the objective is to choose a subset of these guys to maximize the value of the items that you put into the knapsack, subject to the total size not exceeding the capacity of the knapsack. Now, this is a standard NP-hard problem. There is no known algorithm that computes efficient allocation and runs in polynomial time in all instances. There is an FP-TOS, which we can talk about later, but we'll just, for now, I'm just going to make the point that there's no known algorithm that computes efficient allocation and always runs in polynomial time. So let's consider this particular instance, and just again, to illustrate ideas, I have 3 people whose values are 10, 6, and 10, and sizes are 10, 12, and 10. And one of the standard early fast algorithms was Danzig's greedy algorithm, where you sort the bidders by their value per size. So here I've moved the bidders around so that they're ordered by value per size in descending order. And then you pack them from left to right until there's no room. So in this case, you pack the first 2 bidders and you stop when the next bidder doesn't fit, or you can skip that bidder and continue in some versions of the greedy algorithm. And in this case, you get the full optimum. You get a value of 20, and you pack bidders 1 and 2. Now, what about when the values are private and you don't know what the values are to the bidders? You can see the sizes of the item, but you don't know how valuable it is to put the items into the knapsack for each of the bidders. Well, that's not a problem. Here's a strategy proof mechanism you ask bidders to report their values, you run the greedy algorithm using the reported values, and you charge each packed bidder his threshold price. And what's a threshold price? It's the lowest value you could have had that would have gotten you packed. So here we have the threshold prices for the bidders, and that's the mechanism. Now, we're going to use this example to illustrate how profitable investments can reduce welfare. The largest bidder over here, the guy, bidder 3, isn't packed and has a utility of 0. What if he's offered the opportunity to invest? Then he can raise his value from 12 to 14 by investing 1. Well, if he does that, I'm sorry, from 6 to 14 by investing 1. If he does that, that will cause him to be packed. Because 14 over 12 is bigger than 10 over 10, so he'll be packed. And he'll find that profitable because he has a value of 14. He'll have to pay his threshold price, which is 12, and he'll have to pay his investment cost, which is 1. And that's a positive number, so that's profitable for the bidder. But the net investment value goes from 20, which we had without the investment. If he invests, he'll be the only one packed. The value will be 14. He'll spend 1. So the investment will reduce welfare from 20 to 13, and society will be worse off when we include the investment stage. Okay, so this is just to illustrate ideas. The investment can make the algorithm perform much worse than it would have performed without the investment. Okay, so in our general model, the primitives are going to go like this. We're going to look at an allocation instance. I'm going to just look at packing problems for the purpose of the lecture, and I'll talk about the generalizations extensions later. So an allocation instance is going to be a pair of VA, where V is something that's a non-negative vector. It says for each of the n people, what is their value to be included. So for example, if you have planes landing on a runway, what's the value of being able to land your flight, or included scheduled on a machine, or whatever. So we have packing values. It's a vector V. And A is going to be is some subset of the power set of n. It just says which combinations of items can simultaneously be packed. So the knapsack problem is a special case of that. And for example, it could be all sets of bidders whose size sum to less than 10, or all sets of TV stations that can be assigned channels without creating broadcast interference, or all planes that can be landed on a runway, all landed on, somehow scheduled to land on a runway, and so on. And an allocation problem is then going to be, omega is going to be a collection of instances. So, and we're going to assume that whatever the feasible set A is, the set of value profiles is going to be some product of intervals, which means that the possible values for any individual bidder lies in some interval. And an allocation algorithm, or an allocation rule, chooses a feasible allocation for each instance. So you give it an instance v comma a, and it chooses an allocation x of v comma a, which is feasible, so it lies in a. And x of n will be an indicator variable. It'll be 1 if n is packed for that problem, and 0 otherwise. And a payment rule will specify a payment for each bidder, and a mechanism, an economic mechanism, then consists of an algorithm or allocation rule and a payment rule. Now, the way you go from algorithms to strategy proof mechanisms, first of all, remind you, I assume most of you know, that what it means to be strategy proof is that for every instance VA and for every bidder, when the bidder tries to maximize its own payoff, and you can see over here, this is an expression of the bidder's payoff, it gets its value Vn if it's packed. Whether it's packed depends on the problem and what it reports its value to be. And what it pays depends on the problem and what it reports its value to be. And this says that reporting its value truthfully maximizes the expected payoff. And the mechanism is monotone if for any bidder n, there is a packing threshold Tn that depends on everybody else's values or value reports and the feasible set, such that you're packed if your value exceeds the threshold, and you're not packed if your value is less than the threshold. And you can charge, one mechanism you can use is charge each packed bidder a price equal to her threshold. And a famous paper by Lehman et al. Shows that there exists a payment rule P such that XP is strategy proof if and only if X is monotone. And one such rule is the threshold rule itself. You just charge each bidder their threshold price. Okay, now this is important, and so I want to emphasize this. It's not something that you usually emphasize, but the strategy proof payment rule is unique in a certain sense. Here's the sense. If XP is strategy proof, then there exist functions Fn for each bidder n that depend on the other bidder's values and on the feasible set, such that the payment rule in this strategy proof mechanism is equal to the threshold payment plus this function. So this, for those of you who know the Vickrey Clark-Grove mechanisms, they look like this too. There's sort of in the pivot mechanism, there's a standard payment that you make, and you can add anything that's unaffected by the bidder's report, and it doesn't affect the incentives. So this is the entire set of functions that makes the mechanism strategy proof. And so what's important about this is that this term is unaffected by your report. It's clearly what you pay is unaffected by whether you invest. So the investment incentives are entirely determined by this term. And so if XP and XP prime are two different strategy proof mechanisms with the same allocation function, they have the same investment incentives. So for strategy proof mechanisms, you only have to look at the algorithm to determine the investment incentives. The investment incentives are a property of the algorithm once you've specified that you're choosing a payment rule that makes the mechanism strategy proof. Okay. So we're going to look at properties of mechanisms that create good investment incentives, properties of algorithms that will determine the investment incentives. Okay, so here are two notions of efficiency related to allocation and investment. And to describe them, we need notation. So this is the welfare that's associated with mechanism X. When the instance is VA, the welfare that's associated with mechanism X is the sum over the selected items of their values. So that's the welfare that the mechanism achieves. And an algorithm is said to have efficient allocations if for every instance in the problem, the welfare that's achieved by the mechanism is maximal. That is, you choose the set that maximizes the total. And we're going to say that, that investments are efficient as follows. Suppose that bidder n knows B minus n and can invest to change his value. He should profit from that investment if and only if the welfare gain exceeds the loss. So here's the same statement formally. It says that for any instance and any report you might make and any cost that that you might incur from making an investment, the welfare that you get when you invest this, when you spend this cost and you make this and you raise your value to Vn tilde and you report truthfully, that welfare will be bigger than not investing if and only if the social welfare is big, net of cost is bigger than not investing. So that's what we mean when we say efficient investments. We mean you make the same investment decision that the planner would have made. Okay, and for this to make any sense, as I indicated on the previous slide, the bidder has to know what its prices are. It has to know when it makes the investment, whether that's going to result in it getting packed and so on. So there's this is not entirely innocent, but what we're looking at is the idea that we're looking at, landing planes on a runway or something, where you have some idea when you make an adjustment what the prevailing prices will be.
Paul, quick question, clarification question.
Sure.
Here, when you define the efficient investments, we are thinking about investment by a single agent, not a group of agents.
Yes.
Okay. And throughout the talk, should I keep that in mind, or?
Yes, as I indicated at the beginning, there are three ways that even when we talked about BCG, that it could be wrong. The bidder could lack information about V minus N. There could be a coordination problem among bidders, or it could be that there's something different that results from the allocation mechanism. This talk focuses only on that third problem, where it's only investment by a single bidder, and we're looking at how the algorithm affects that, and not at the other two problems, which are important problems as well. Okay, so Vickrey-Clark-Grove mechanisms yield efficient investments. They're efficient and strategy proof and in allocations and investments. And this is an old result of Rogerson from 1992. But non-optimizing algorithms, we know don't. They can have what these algorithmic externalities, which means that necessarily the threshold prices fail to reflect the full social cost. And what we want to know is for which allocation algorithms do threshold prices internalize the externalities and lead to efficient investments? That's the first question that we're going to ask. Later we'll talk about near efficient investments, but right now we're asking about efficient investments. And so we're going to need a weakening of the notion of efficient allocations. We're going to speak of range efficient allocations. We're going to say that the algorithm X chooses something that's efficient in a range if basically there is a subset of the feasible allocations, such that the welfare that you get from using X on every instance is maximal over that subset. So the range is something that's a property of X. It can depend on A, but it can't depend on V. So the greedy algorithm for the knapsack problem does not use range efficient allocations. And the theorem is that for any mechanism with a monotone X, if it has efficient investment incentives and it's strategy proof, then it uses range efficient allocations. So basically, the only way you're going to get efficient investments together with strategy proofness is that you have to be able to maximize over some restricted set. And in computationally hard problems, that's not always a good idea. There are some problems where it might be a good idea, but there are many where it's not. So, so we don't expect a lot of the good approximate rules to have this property, to have the efficient investment property. Okay, so to recap where we are so far, monotone algorithms can be made into strategy proof mechanisms. And for these mechanisms, investment incentives are entirely determined by the algorithm. They're a property of the algorithm rather than which payment rule that we chose. Algorithmic externalities can lead to inefficient incentives. And the only algorithms with efficient investments are those that exactly optimize, possibly on a restricted set of allocations. And we want to look at algorithms that are in a broader class than those. Okay, so the next question was about approximate investment incentives, and this is where I think most of the interesting and more surprising results are. So suppose we start with a monotone algorithm and we create the corresponding strategy proof mechanism. And we know already that if it has efficient allocations and it's strategy proof, that it leads to efficient investments, that's the VCG theory. Is it true that if we have nearly efficient allocations, if we have something that's a good approximation, that it provides incentives for nearly efficient investments, whatever that means? Okay, so let's give some meaning to those words. So we're imagining that we have an investment technology in which the investor can either have the value V lower bar n at cost 0, makes no investment and that's his value, or he can have the value V upper bar n at some cost C bar greater than or equal to 0. We'll call that thing an investment technology and denote it by I sub n. So given this investment technology and the bidder's threshold price, the bidder chooses an investment to maximize his payoff under the strategy proof mechanism. So this B star is the set of choices that the bidders can make to maximize his expected payoff. So when he chooses VNC, he's going to incur a cost of C. He's going to have values VN. He's going to report it truthfully because it's a truthful mechanism. And this will be the value he gets minus the price he pays minus the cost. And we're going to say that this will normally be a singleton, but just to cover, to treat the general case, we're going to put a bar over welfare for investment problems. So remember, welfare for the basic allocation problem, we fixed the values of the others and the feasible set and the value of bidder n. Here, when we put a bar over it, we change the first argument to the investment technology and say that the welfare with the investment technology and these other variables held fixed. And in case there are multiple optima, we're going to look at the worst one since we're looking at worst case guarantees. So we'll minimize over elements of B star. Now, normally, again, B star will be a singleton. So it'll be either better to invest or not. So this is just here for specificity. Okay, so what's our benchmark going to look like for efficient investments and efficient allocations? So if we're using the efficient choice rule, then what we would do, given an investment technology and given values and the rest of the problem, we would maximize the welfare. And so we'd incur a cost of C if we chose the cost of C. And here is the welfare that results from the efficient allocation when the values Vn and the other values are V minus n and the feasible sets A. So we just maximize that and call that the welfare of the optimal welfare of the investment problem. And an algorithm X is a beta approximation with investment. If for every investment instance, the welfare that you get when you're using allocation rule X is at least beta times the optimal welfare. Okay, so looks a lot like the way you would define it for the allocation problem. So this allows that you could be making inefficient investments provided that the welfare net of investment is at least beta of the first best welfare. Okay, so how do investments affect the guarantees of an algorithm? Well, they can't get better. When you add the possibility of investment, you might make things worse. So for any beta, if X is not a beta approximation in the allocation problem, then it's not a beta approximation with investment. Because the investment problem could just be you invest 0 to do nothing. And the second proposition says that things can get a lot worse. For all beta less than 1, there exists a beta approximation for the knapsack problem that's a 0 approximation for the problem with investment. So beta approximations plus strategy proofness do not imply anything close to beta approximations with investments. And you're going to be interested, of course, in the second of these propositions. So here's an example of how bad things can be. And this is a satisficing algorithm. So we've got bidders that we're going to pack in a knapsack, bidders 1, 2, and 3, and so on. And if bidder 1's value exceeds 99% of the total, then pack that bidder. Otherwise, optimize exactly. So that's an algorithm. So suppose we have 2 bidders and suppose there's space for both of them in the knapsack. and their values are V1 and V2. Well, if V1 over V1 plus V2 is bigger than 0.99, then we pack bidder 1. And if it's not, we pack both of them. Okay, so this is an algorithm that has a 99% guarantee. Bidder 1's always packed, so her threshold price is 0. Suppose that her investment technology is she can have a value 0 at a cost of 0, or a value of k plus epsilon at a cost of k. It's going to be profitable for this bidder to invest. She's always packed, and she's going to raise her profits by epsilon. And if k is large, only bidder 1 will be packed, and the welfare will be k plus epsilon minus k. It'll be epsilon, and the first best welfare is V2 plus epsilon. The approximation ratio with investment, therefore, is epsilon over V2 plus epsilon, which is arbitrarily small. Okay, so for this satisficing algorithm, which guarantees 99% of the value in the allocation problem, it has a 0 guarantee in the problem with investment. Okay, so and by the way, the canonical fully polynomial time approximation system also has a 0 approximation with investment, much harder to show. So I'm not going to put it up on this slide, but this is, let's consider the satisficing algorithm. What's special about it is that this algorithm has what we call a Bossy negative externality. Now, in the current version of the paper, we distinguish 2 types of externalities that a mechanism can have, that an algorithm can have. It can have what we call a threshold externality, which means that when if you invest in a way that causes your value to cross a threshold, you have an effect on the total welfare, and your price might not be equal to the effect on that welfare. And that means there's an externality that's associated with crossing the threshold. And there can also be what we call a Bossy externality, which is when you make an investment that doesn't affect your own allocation at all, but does affect what the algorithm chooses. That's called a Bossy externality, because you're doing something, you're making a report that doesn't affect what happens to you, but does affect what happens to others. And this algorithm has a Bossy negative externality. When you raise the value from 0 to k plus epsilon, it doesn't change whether bidder 1 is packed, but it reduces the welfare of bidder 2. Okay, and so that's what we call a Bossy negative externality. And so the theorem is going to be that for any beta, if X has no Bossy negative externality, if it excludes Bossy negative externalities, and if it's a beta approximation in the allocation problem, then it's also a beta approximation in the investment problem. So, so we need to see what is X bound. This is what it means to exclude Bossy negative externalities. If you take any allocation instance, VA, and any alternative value, Vn prime, and if n would be packed in this value, and Vn prime is bigger, so that means that n is still going to be packed because this algorithm is monotone. So when you make this investment, if you make an investment raising your value from Vn to Vn prime, it's not going to affect whether you're packed. You're packed in both instances. And here's where you're not packed with V, and maybe you're making a disinvestment. You're saying, I'm going to cash in on this asset and just sell it, or scrap it, and the value goes down, but you weren't packed anyway. So that action has no effect on whether you're packed, but might affect what the algorithm does to others. And it says, so in these 2 cases where you make a change that doesn't affect whether you're packed, the total value that everybody else gets can only go up and can't go down. Okay, that's what this says. So the Bossy negative externality is when you're packed and you increase your value, or you're not packed and you reduce your value, and if that causes the total value of the allocation to others to go down, that's a Bossy negative externality. And excludes Bossy negative externality says that never happens. So for any beta, if X excludes Bossy negative externalities and is a beta approximation for the allocation problem, then it's still a beta approximation for the investment problem. So you might wonder whether there are any algorithms like this. And the answer is yes. So first of all, exact optimization is Xbone. If you run the greedy algorithm and you keep running the algorithm until nothing else fits, that's Xbone. If you increase your value and you would have been packed and move up higher, it doesn't affect anybody else who's packed. And if you wouldn't have been packed and you move down lower, it doesn't affect anybody else's packed. So greedy satisfies Xbone. If you have a bunch of Xbone algorithms and you run several of them and take the maximum of them, that will be Xbone. And in particular, this algorithm where you run the greedy and then you also consider packing individually the items, call that smart greedy, that's Xbone because it's a maximum of Xbone algorithms. If the algorithm is not bossy at all, that is if changing your bid without changing your allocation doesn't affect anyone, that of course is Xbone. The algorithm we used in that's implicit in the greedy rejection algorithms that were in the FCC reverse auction for packing television stations, that was Xbone. And if you have an algorithm that's monotone and Xbone, it's going to have this property called bitonic that from Ulam and Nissan 2008. And again, the theorem is that for any beta, if X is Xbone and a beta approximation for the allocation problem, it's still a beta approximation for the investment problem. Okay, and what have I got here? So the intuition is going to be that in a approximate algorithm, threshold prices don't necessarily reflect the social cost of packing the bidder. And the way the argument is going to work is that we're going to decompose the change in value in a mechanism. Consider an investment that moves a value to just cross a threshold at a tiny cost. Well, that can make things worse, of course. We've seen an example of that with the greedy algorithm, but there's an instance of the allocation problem that has equally bad performance. So in the greedy algorithm example I gave you, if that guy's value were 13, it would have had the same performance as it had in the investment problem, where it raised its value to 14 by investing 1. Okay, so there's going to be something in the allocation problem that's just as bad as your investment problem when you cross the threshold. Investments that reduce worst case welfare by value changes that do not cross a packing threshold, if they reduce worst case welfare, they have to do it by value changes that don't cross a packing threshold, and those are what we call the Bossy externalities. And in a strategy proof mechanism, those changes that you cause are not priced at all. The individual's price is unaffected by the investment that the individual makes. So the individual will have the wrong incentives. So Xbone is something that forbids harm to other bidders from exactly those kinds of changes. Okay, that's sort of the intuition. And we're going to sketch a proof now to give you an idea of how it goes. So we're going to start with any instance where here's the investment instance and the values of the others. And below, I'm going to suppress V minus NA. I'm not going to vary that at all. In the problem, we're going to be focusing on the investment. So I faded it out here and left it entirely out of the arguments below. V minus NA is being held constant on this slide. Okay. And we're going to take any instance in which the investor is not indifferent. We're not going to have multiple optima for the investor and suppress that dependence. And now there's two possibilities that we want to start with. If Vn bar minus C bar is less than Vn, if by investing you can increase your value but not even recover the cost of doing so, the investor is never going to choose to make an investment like that in any mechanism. And that's the efficient choice, so we're not worried about those. we're not going to make things worse by including investments like that. So we're going to focus on the case where by making an investment, you can increase your value by more than the cost of the investment. And we're going to make the important observation that in the optimum problem with this investment, that's the same as looking at an allocation problem where the value of packing this bidder is Vn minus C bar. Okay, so we're going to use this equation down below, that the value in the optimal investment problem is the same as the value of the optimal allocation problem using the value Vn minus C bar. Okay, so again, if V bar minus C bar is less than Vn, we'll have the investor make the efficient choice, and otherwise we'll have this equation where the argument of the allocation welfare is the welfare using the net value. Okay, so there are two cases to consider. In the first case, the bidder would have been chosen if his value were Vn bar minus C bar. This is exactly the key. Remember, if the bidder would have been chosen, then his threshold price is the same if he raises his value to Vn. So the threshold price is unaffected. So if the bidder would have been chosen here, this would be a profitable thing for the bidder. So the bidder will choose this. He'll raise his value, he'll pay the cost of C bar, and he'll have the same allocation that he had here by monotonicity of the algorithm. And so we can make this argument. What we want to do is we want to start with beta times the efficient welfare and show that that's less than or equal to the welfare we get under X. So we do it this way. This is beta times the efficient welfare of the investment problem. Here's the equation I showed you before. That's the same as beta times the allocation welfare in the problem where the bidder's value is Vn minus C. And the next inequality is because this is a beta approximation of the allocation problem. So beta times the optimal welfare is less than or equal to the welfare under X. And the next step is to it uses Xbone. And what we have here is that X is monotone. So if the bidder was packed, it continues to be packed over here. So his welfare is going to be Vn bar minus C bar over here, and that bidder's welfare is going to be Vn bar minus C bar over here too. And everybody else is not worse off from this change, according to Xbone. So we get this inequality here. And this is equal to the welfare of the investment problem. And so we have a string of equations and inequalities that tells us that beta times the optimal welfare in the investment problem is less than or equal to the welfare with X in the investment problem. And you can do a similar thing on the for the case of where the bidder is not packed. Okay, and I'm not going to go over that in detail. It's the same, qualitatively the same kind of argument. All right. So let me press on a little bit then. Subproblems can have better guarantees. We're going to say that an allocation problem omega prime is a subproblem of omega if it's a subset. It's a problem itself, but it's a subset of the problem omega. And approximation ratios can only improve on subproblems. Some of the worst case may not appear in omega prime and does in omega. So for example, in the greedy algorithm, in the knapsack problem, if no bidder's size exceeds 10% of the knapsack's capacity, the greedy algorithm on that problem is a 0.9 approximation. Okay. And a corollary of our theorem is that if X is Xbone on omega, then for any subproblem omega prime and any beta prime, if X is a beta prime approximation on the subproblem, then it's a beta prime approximation with investment on the subproblem. This is just a simple corollary of the previous result. And the reason it's interesting is a lot of times, you know, we do for when we're working on algorithms, worst case analysis, and but we expect that the algorithm performance is really going to be better than the worst case analysis. And we expect it's going to be better because we're going to be working on a subproblem where we're not going to have such, coincidentally terrible selections of the values. And then you might think, okay, well, I'm really trying to get better performance on the investment problem too. And this says that if you can guarantee on any subproblem that the allocation performance is better, then the same thing applies to the investment performance. Okay. Now we have the last main result is a characterization theorem. The question is whether exponent is necessary. We've shown that it's sufficient, and it's not quite necessary. But the theorem says let X be a beta approximation on a set of problems for some positive beta. Then the following two statements are going to be equivalent. X is weakly exponent, which I will define on the next slide. And for every subproblem omega prime and every beta prime, if X is a beta prime approximation on the subproblem, then X is a beta prime approximation with investment on the subproblem. So if X is not weakly exponent, then there's some subproblem such that the approximation gets worse when we add investment. So what's weakly exponent? We think of exponent as being almost necessary. Weakly exponent is a much uglier condition, and it looks like this. Okay, exponent can be relaxed for certain kinds of downward changes. We don't actually need the, so remember exponent was previously defined without the red stuff in here. This is what's new in the definition of weakly exponent. So we have somebody who's not packed and is in every efficient allocation, and the bidder is reducing this value. So what you'd need to know to check weakly exponent is you'd say, well, if n was in every efficient allocation anyway, then we don't need to impose that there's no Bossy negative externalities. Now, of course, checking that n is in every efficient allocation in a problem that's NP hard is not something we expect to be able to do. So, while this weakening of exponent gives us a necessary and sufficient condition, it's not a checkable condition. Okay, in problems of interest, we're not going to be able to compute the efficient allocations. Okay, so I've described this for packing problems. The results can be extended to cost minimization problems, traveling salesmen, Steiner tree problems. It also extends to problems with multidimensional types in which there's different ways you could be packed. You could put a small plane on the runway or a large plane on the runway. Efficient investments still require exact optimization. And there's a generalization of exponent, which is still just a property of the algorithm that suffices for the guarantees to be robust to investment. So, and it extends to combinatorial auctions with XOS preferences with a restriction on investment costs. So if you want to restrict investment costs in a particular way, we have a variety of restrictions, but basically the exponent appears to be a critical condition for algorithms to satisfy to imply efficient investment incentives in the worst case. So to conclude, in a strategy proof mechanism, efficient investment incentives require exact optimization, and for many problems that's infeasible. VCG requires that you take differences of two maxima. The prices that you're estimating may be much smaller than the maxima. Tiny percentage errors can lead to huge errors in pricing. You can't really implement a Vickrey mechanism on those kinds of problems. Approximate algorithms that choose near optimal allocations can be far from optimal with investments if the algorithm has Bossy negative externalities. If the algorithm excludes Bossy negative externalities, then its guarantee on any subproblems remains the same for the investment problem as for the allocation problem. And it is possible to weaken exponent a little bit, but it involves checking whether a condition holds on a set of optimizers, which is going to be very hard to check. So we think exponent is the condition we're going to be looking for. And that's my talk.
Thank you so much, Paul, for the great talk. We have a few questions already. If you like, let's move on to questions. There is one in Q&A, and I think Martin has a question as well. Martin, you can go first if you like, and then I'll relay the question in the chat.
Sure, I'll be happy to. Well, thanks, Paul, for a very inspiring talk. I think investment incentives is indeed something that has often been overlooked in market design. So this is very thought-provoking. So much of your talk has looked at mechanisms for single-minded bidders, right? So you have monotone mechanisms and thresholds. There has been some work on truthful in expectation mechanisms for general valuations, like those are in this broader framework of relax and round. So you essentially relax the integer program, do some rounding techniques, and then you apply a VCG type of mechanism. And that also has truthfulness properties, like truthful in expectation, a randomized notion, essentially, if you like, for these types of mechanisms. And I was just wondering, probably the investment incentives for those would be extended to kind of randomized investment incentives in expectation as well. But I was just wondering if you had any thoughts on those types of mechanisms.
Wow. So I'm actually not familiar with those types of mechanisms. So the randomness is that you randomize over nearby points. Is that what you do? What do you do exactly in those mechanisms?
Essentially, what you do is you take the integer program, you relax it, and then you do some rounding tricks, as is often being done in integer programming, right? And then based on so this is really a random choice of an allocation in a way, and then you pull on a VCG type of payment rule to set incentives. So one example would be a paper that goes back to, I think, 2011 by Ron Lavie in the Journal of the ACM. So that it again uses VCG. So I would expect that it has at least some investment incentives in expectation. I was just wondering if somebody has looked into those.
No, we have not looked at those, and I hesitate to speculate. So you could invest and be included in some and not others of these allocations because of the way the randomization works. No, I don't have an intuition actually even for how that would work. You know, we even as we emphasized, one of the things that we put down is that you needed to know V minus N. We're looking at something where people know the prices. You know, so we were eliminating other sources of randomness in order to make our arguments. And I don't know how the source of randomness you're talking about would enter into the argument.
Thank you.
All right, there's another question. I'm going to unmute Vitor, and he's going to ask his question.
Yes, hi. Yeah, so my question is about these investment technologies. So in the example that you presented where there was this zero approximation, right?
Yep.
The key that makes the construction work is that the investment is like very inefficient, right? So for K plus epsilon cost, you basically get epsilon increase in your own utility. But what if there's like some kind of ratio, you know, like that the investment has a minimum and efficiency factor of 2, just as an example, right? So for K investment, you get kind of 2K additional utility. So that's kind of constraining the set of possible investments. And with this condition, which strikes me as similar as Exponent or something, could you show some approximation guarantees?
So, well, I mean, you're asking an interesting question. Certainly, if if you impose restrictions on investments that they have to be extremely valuable, the worst case guarantees won't be affected as much. then you'd want to match that. Presumably you'd need to match that to the efficiency of the algorithm itself. Remember, I was going for a zero approximation there just to show how bad things could be. I suppose that with the condition that you described, the worst case would still get worse. It would still be the case that worst case investment performance would be worse than worst case allocation performance. But if you impose some restrictions on investment, it probably wouldn't fall all the way to zero. Remember, I intend that merely as an illustration of how bad things can be in the extreme. And I put that up also because it's a really simple example. The fully polynomial time approximation system for the knapsack problem also has a zero guarantee with investments, as we show in an appendix to our paper. So yeah, so you would need some restrictions to achieve anything reasonable.
Yeah, thank you.
Perfect. If there's a final question, we have time for maybe one other brief question. Please raise your hand on the chat. Sorry, raise your hand or type your question in the chat. Okay.
Okay.
All the questions. Thank you so much for a super interesting talk, Paul. Thanks for accepting our invitation and kicking off our winter seminar series.
Thanks for inviting me, and enjoyed the talks that are coming up. Looks like you have a great lineup.
Thanks a lot, Paul.
Sure.
Thank you, Paul.
Bye-bye.
Bye, everyone.
Bye-bye.